Hey guys, today we're going to be taking a look at a few properties of determinants, and before watching this video, I'm hoping you know what a determinant is and how to solve for it. I also am hoping that you are well comfortable with solving matrices, how they look, and properties of determinants are really helpful when you have determinants larger than the order of 2, for example, when you're dealing with square matrices. So finding the determinants for a matrix in the order 2, such as, let's say we have a matrix 1, 2, 7, negative 8, finding the determinant for that is pretty simple, right? We just have 1 times negative 8 minus 7 times 2, and then we just solve for that, and we get our determinant. But in some cases, we're not going to have such a simple matrix to deal with. In some cases, we're going to have a lot of matrices, like a lot of elements in a matrix. So we have, like, for example, 9, negative 7, 4, 3 halves, 0, negative 1, negative 4. I'm just making these numbers as I go. 7, negative 9, and 8. And in this case, we can't just do the simple formula like we did for a square matrix of order of 2. And properties of determinants just kind of settle it down easier for us to find the determinants of these. So let us just simply erase that. So before diving into the properties of determinants, I'm first going to tell you about this C notation. So this C notation is nothing but the cofactor. And now there are 2 main properties not to know for determinants. One of them is cofactor, the other is minor. But for right now, I'm just going to focus on cofactor since that appears more in determinants rather than a minor. So cofactor is best understood with an example. So let's say you have a matrix that is 1, 2, 3, 4, 5, 6, 7, 8, 9. So a very generic square matrix of the order 3. And now we have to find a cofactor of, let's say, the first term. So the cofactor of the first term is going to be nothing but the negative 1, and then it's going to be row plus column. So 1 is in the first row, it's in the first row right here, and it's in the first column. So we're going to do 1 plus 1, which is 2. So we're going to have negative 1 to the power of 2. And times, now this is where it gets a little bit tricky, but you see that 1 is in the first column and in the first row. So now we're going to pretend that the first column, aka this, never existed, and we're going to pretend that the first row never existed. Now, let us just erase this part. Let's say that never existed. Now what we are left with is just this. So we're actually just going to rewrite this as it is. So what this is saying, this is basically saying 1 times negative 1 squared times the determinant of this sub-matrix that we got from our original matrix. Now that is the cofactor. Now to put it in more general terms, let us say we have a matrix A, and that is equal to A11, A12, A13. And where am I getting these notations? Well, usually when we're talking about matrices and determinants, we usually use this notation where I is the row number and J is the column number. So for this one, for example, I know that this is in the third row and the second column. So that's why I write it as A32 or A32. It doesn't really quite matter. Alright, so now we have our matrix. Let's see the general formula of finding a cofactor. So for finding a cofactor, let's say we want to find the cofactor of this term right now. So finding the cofactor of A12, we're going to take that term, we're going to multiply it by I plus j. So I plus j, this is basically saying the row, and this is saying the column, right? J is always the column, I is always the row. That is the notation we use when we're dealing with determinants and matrices. And then we're going to find the determinant when we pretend this column didn't existed, and we pretend this row never existed either. Now what we're left is just this. So we're going to write it the same exact way, So then we're going to write it as A21, A23, A31, and A33. So this takes some time getting used to when you're solving problems. It may take a lot of time to remember this whole entire formula, but as you solve more problems, it becomes much easier. So I'm going to apply that same exact thing to our properties of determinants. I just wanted to bring up cofactors since they are an important part when we're talking about determinants, and they're almost in every single property of determinants we're going to see after this property. And yes, it looks a little cryptic, but let's break it down. So we know that Ij is the current, that's really bad, is the current element we are on. And we know that this, as I just explained, is the cofactor of the current element we're on. And of course, this is better understood with an example. So let's say we have A is A11, A12. So okay, let's assume that is the matrix. Now what this is saying is that the determinant of that matrix, this is the notation for a determinant. Now the determinant of that matrix is equal to, let's say that we are looking at this row right over here. This is basically saying that let's take the first element of the first row, so that's going to be A11, and we are multiplying over here, so times the cofactor of this term, and we just looked at cofactors, right? So we're just going to say cofactor of that term plus, because now we have to do that for the other two elements in that row, plus that element we're on times the cofactor of that same element, C12, plus this element we're on, A13, times the cofactor of that. And that will give you your determinant. Likewise, it doesn't always have to be the row. We can also have it in columns. So once again, let us have the determinant. And let's say now we are using this second column. All right, this second column. What's the first element in that column? Well, that's A12. So this is saying A12 times the cofactor of that element plus the second term in that column, A22 times the cofactor of that element, plus, and the final element is A32 times the cofactor of that element. And that will give you your determinant for that matrix. So the main point here is that you need to stick with one column or either one row. You can't have one element here, and one element here. No, it has to be in a column or in a row. All right, now on to the second property. The second property is very similar to the first property, but where in the first property we were taking the cofactor of that of that element we were on. In this case, it's a little different. In this case, we have something K. So let us take an example. Let's take the example for the first scenario. So let's say, once again, we have that matrix A. So this is our matrix. And now what this is saying is that the determinant, let's say we're using the second row now. We're using the second row. In this case, let's take the first one as it says right over here. So that is A21 multiplied by not the cofactor of this element. You see there's a K over here. Now let's say that K is 1. And what that is basically saying is that we're going to take the element right above it. We're going to take the cofactor of the element right above it. Why? Because this we know is A12. It is in the first column. Likewise, we're saying that K is 1 and J is 1. J has to be 1 because in this case we're saying the element we're on is currently 2, 1, right? And you see that over here and over here, J has to be the same. So J is indeed the same. The column has to be the same. We are simply just changing the K value. K value, we're saying, okay, let the K value also be 1. So in this case, we're just going to go up 1 and take the cofactor of this. Now, you might be saying that, hey, the K value could also be 3, right? Like we could still be in the same column and go down 1 row. Well, that is exactly correct. It just matters what value of k you're going to use, what row you're going to use, what row you're going to take the cofactor of. So in this case, let us, well, as you pointed out, let us just use 3. So let's say that k is 3. So in this case, we're saying k is 3. So then we take the cofactor of 3, 1, plus, we go back to the next element of that second row, a2, 2, and then since our k is 3, we go to the third row, and the same column, it has to be the same column, a3, 2, plus, next term, a2, 3, multiplied by the element right below it, a3, 3, because k is 3. And that will be our determinant. Likewise, you don't always have to choose a row, right? We saw in the last one you can also choose a column. We chose the second column, I believe, for the last example. So let's do the same thing. Let's choose this column right over here. Now we're talking about this scenario here. So this is A is equal to, once again, it's pretty obvious we have to take the element of the column we're on, so A1, 2. Now for the cofactor, this is saying that, okay, the row this time has to be the same. The row this time has to be the same. It's just that the column is changing. All right, let's go to the third column. All right, so the row still has to be the same. So we're still going to be focusing on the first row because that's where our first element is in. But now we're just going to go to the third column. So the third column is over here. Same row, third column. That aligns with A1, 3. So cofactor of A1, 3 plus the next term, A2, 2, multiplied by the cofactor of the term in the same row, column being 3. So cofactor, C2, 3. And finally, last term, A2, 3, A3, 2, excuse me, times the cofactor of this term right here, AC3, 3. And that is going to be our determinant. Alright, so now to our third property of determinants. The value of a determinant remains unchanged if its rows and columns are interchanged. So I have an example to the right. There is a matrix A and I just populated it with some values. It is a square matrix of order 3. And let's say the determinant of this matrix is just A, right? Because that is how we represent a determinant of a matrix with these lines, right? So now let's say we have another matrix, and in this case we just interchange the rows and columns. So the first row will become the first column, the first row will become the first column, the second row will become the second column, and the third row will become the third column, so 2, 3, negative 7. And if we take the determinant of B, that will actually be the exact same as the determinant of A. Alright, so now on to property 4. If any two rows of a matrix are interchanged, then the value of the determinant changes by a minus sign only. So once again, on the right, I have the same exact matrix from before. Now let us change two rows. Let us interchange two rows of that matrix. So let us say that the new matrix, let's interchange the second and third row. So let's interchange the second and third row. So this is the second row and this is the third row. So nothing happens to the first row. So now we interchange them. So this comes over here, third row goes on top. Third row goes on top, so we get 2, 3, negative 7. Second row comes at the bottom, so we have 4, 9, 1. And if we found the determinant of A to be, let's say A, then the determinant of B, well, the property 4 says changes by a minus sign only. So the determinant of B would just be minus A. And that is only possible when we switch to rows. Now for the columns, very similar when we switch the columns. So in this case, let us switch let me erase that. Let us switch the second and third column. If we switch the second and third column, this is the second column and this is the third column. Once again, the first column stays as it is. Interchanging this and this, we get 3, 1, -7, 7, 9, and 3. And the determinant of b, well, as it says, changes by minus sign only, which is -a. So, the key takeaway from this is that one thing you cannot do is that you cannot simply take the first row, for example, and interchange it with the first column. That is not this property. This property is saying you can only deal with 2 rows or 2 columns, not 1 row or 1 column. You need to deal with, as we saw here, we just dealt with columns. In the previous example, we just dealt with 2 rows. So it can either be rows or columns. Then only this minus sign will take effect. Property number 5, if any 2 rows of a matrix are identical, then the determinant is 0. So let us take a look at this one. So we see that the first row and the third row, they are identical. So that's pretty easy. The determinant of that would just be 0. And that is so much more helpful than calculating the determinant of a 4 by 4 matrix. Because if you had like a 10 by 10 matrix and you saw that, okay, these 2 rows look similar, they're exactly the same elements at the exact same spots, then okay, then you automatically know that the determinant is 0. Same thing over here. If any 2 columns of a matrix are identical, then the determinant is 0. We see that the first column and the third column, they are exactly identical, so the determinant of matrix B is 0. Property 6. Let A equal Aij, and that is a square matrix of order n, and let B be the matrix obtained from A by multiplying each element of a row or column of A by a scalar k, then determinant of B is equal to k times the determinant of A. So of course that is a lot of words. Let's put that into perspective with an example. So on the right side, I have a square matrix of order 3, and what the property on the left side is saying is that multiplying each element of a row or column by a scalar k. Let's assume that scalar k is, I don't know, -4. Let's say that is -4. Now, let us multiply that scalar k by any column or row you choose. Let's say we choose the first column. Alright, so let us multiply -4 by the first column. So we have -4 times 1, and then 2 and 3 stay the same. We have -4 times 4, and 5 and 6 stay the same, and we have -4, whoops, wrong color, times 7, and 8 and 9 stay the same. So we multiplied k, so we multiplied -4 or k with the first column. Now, let's say we are asked to find the determinant of B. Well, the determinant of B will be nothing but k, which is -4, times the determinant of A. And this determinant of B can also be written as that. So pretty straightforward. It does not matter which column or which row you multiply that scalar k with. It just has to be consistent. Like if you're going to do it for the first column, make sure to do it for every term in that first column. Now on to property 7. If each element or row or column of a matrix is expressed as the sum of 2 or more terms, then the determinant can be expressed as a sum of 2 or more determinants. For example, we have A, which is a matrix on the right side. Once again, square matrix of 3 by 3. Once again, all these properties can be applied to larger matrices. I just find 3 by 3 more simpler and easier to wrap your head around. So we have A, and we see that the first column is actually a sum of 2 terms, and that is what we need, sum of 2 or more terms. I just did 2 terms for simplicity's sake. So we have A plus B, C plus D, X plus Y. And what this is saying is that the determinant of A, and this is supposed to be a matrix, the determinant of A can be expressed as a sum of 2 or more determinants. That's basically saying Determinant of A is also the determinant of A 2, 5, C 3, 6, X 4, 7. Can't fit that in one line, but plus B 2, 5, D 3, 6, and Y 4, 7. Now basically what I did, I just took this, and this, and put them all in one matrix, and I have to find the determinant of that. Plus taking this, and this, putting them all in one matrix and finding the determinant of that. And overall, if you add those two, that will be your determinant of that original matrix. Now on to property 8. If each element of a row/column of a determinant is multiplied by the same constant and then added to the corresponding elements of some other row/column, then the determinant stays the same. So what do I mean by this? Well, let's say we have an original matrix A, and that is A, B, C, D, E, F, X, Y, Z. And let's say that the determinant of that matrix A is denoted as A, right over here. Now let's say we have another matrix B, and that's where we're going to apply this property. So this property is saying if each element of a row, so in this case, I took the row, or in this case it says row/column. In this case, I took the column B is multiplied by the same constant. In this case, the constant is K. So let's say that constant is K multiplied by K. So if I multiplied K times B, that is just KB. If I multiply K times Z, that's KE. If I multiply K times Y, that's KY. Constant, and then added it to the corresponding elements of some other row/column. So since I took a column before, I have to take a column again. I can't take column and then pick a row. I have to stick with one thing, row or column. In this example, I'm doing a column. So I add them to the corresponding elements of another column. Now I just took this column, and now I will add this to that column, which is what I did over here. So I did A plus KB, D plus KE, and X plus KY. Of course, you could have chosen a different column to start with and then multiplied a different constant with that column. For example, you could have chosen this column, multiplied that by K, and then added it over here. But the point is, even if you multiply a column or row by a constant and add it to another column or row, the determinant will not change, which I think is pretty cool because you perform so many operations and still the determinant is still the exact same. So now on to property 9, another really helpful property. If each element of a row or column of a matrix is 0, then its determinant is 0. So once again, I have an example matrix towards the right. I see that, okay, the third row over here, every element in the third row is 0. And according to property number 9, that determinant must be 0. And this is true for both rows and for columns. For our 10th property, if A equals Aij, meaning that it is a square matrix and it is a diagonal matrix of order n, where n is greater than or equal to 2, then this is its determinant. Now, what many of you may be thinking that, oh, okay, if I have like A, B, C, let me use another marker for this. If I have, for example, A, B, C, D, E, F, and then X, Y, Z, then I would say, okay, well, that's really simple. The determinant is just the determinant is just simply going to be A times E times Z, because that's what it's saying, right? A11, which is this, A22, which is this, A33, which is this, all the way up to A and n is greater than or equal to 2, and in this case is 3, because you have 3 rows and 3 columns. That must be the determinant. That is wrong. The main point to take away from this is the diagonal matrix. Now, this is not a diagonal matrix. It is far from a diagonal matrix. A diagonal matrix is going to be something like this. A diagonal matrix is where you have a matrix and you have 1, 0, 0, 0, 7, 0, 0, 0, negative 19. This is a diagonal matrix. In more formal terms, a diagonal matrix is nothing but a matrix where just its diagonals are filled and everything else is 0. So when we're talking about diagonals, the diagonal is always going from the top left to the bottom right. If you had something like, let us choose B, if you had something like 0, 0, 1, 0, negative 2, negative 7, 0, 0, then this is not a diagonal matrix. It has to go from the top left to the bottom right, and everything else besides this part has to be 0. That is what a diagonal matrix is. To see this in a 2 by 2 form, that would just be like that. So starting from the top left, ending from the bottom right, everything else is 0. So that is a diagonal matrix. Now, if we use A for our matrix, then the determinant of A, we can absolutely do 1 times 2 times negative 19. And this is only applicable when it is a diagonal matrix. Alright, now for our 11th property, if these should be capital. So if A and B are square matrices of the same order, then A times B and the determinant of that is equal to the determinant of A times the determinant of B. And this may seem really obvious in a sense, but what this is meaning to say is saying if you have a matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and you are multiplying that by, let's say, negative 7, negative 9, negative 4, 3, 0, 1, 8, negative 7, 8 once again, and you're trying to find the determinant of that, well, that is just equal to the determinant of these matrices separately. So that is just saying determinant of the first matrix, like that, times the determinant of the second matrix you had. Determinant of that second matrix you had. And now for our last property, let A be a square matrix of order n, and let Cij be the cofactor of Aij in the matrix A, and previously we talked about cofactors, so that is going to be helpful in this property. If C is equal to a matrix Cij, and that's the matrix of cofactors of elements in A, then the determinant of C is equal to the determinant of A to the power n minus 1. So once again, this is best understood with an example. So we have a matrix A, and we have a few terms. It's a square matrix of order 3. So n is going to be equal to 3. N is going to be equal to 3. And then once again, C is basically saying that, okay, the first term is going to be the cofactor of the first term in matrix A. The second term is going to be the, this is supposed to be 2. So 1, 2. The second term is going to be the cofactor of the second term in A. And likewise, if we have C23, this is basically saying C23 is going to be the cofactor of A23 in matrix A. And once again, if we know the determinant of this right over here, determinant of A, let's say that is equal to A, then we can know the determinant of C, which is going to be A to the power n minus 1, as it says over here. And we know n is 3, right, because it is a square matrix of the third order. So that is basically saying determinant of C is also determinant of A squared, because you do 3 minus 1 squared.